Hello everyone, welcome to episode 4 of DiffyQ and Linear Algebra with Sensei Kernel Mathematics. Today we're going to be looking at algebraic properties of solutions. Please don't mind that I have not uploaded in 6 days. I've been a little busy, and I promise it's not just because I fell off, but today's episode is going to be a bit weird. I'm going to be going into a lot of nitty-gritty detail about stuff that might be a bit unfamiliar to you. So if you have any questions, please do not hesitate to comment or email or anything like that. Let's get into it. Here's the second order homogeneous equation. So basically, here he is. If you think it looks scary, or if you think it looks easy, I'm going to tell you right now, if you think it looks scary, you are on the right track. This is a lot different from our first order differential equation, and these are generally very, very much more difficult to solve. Also notice that I am rewriting how I do the derivatives. It's easier, just easier for me to type like this. Probably easier for you to see too. But luckily there are certain types of second order differential equations that we can look at. A big word that I want you guys to learn today is linearity. If it is a linear second order equation, it is going to be a lot easier to solve. There are some tips and tricks and properties that we can use to our advantage, and I'm going to show you guys a lot of those in this video. Let's get started. First things first is the existence uniqueness theorem. P of t and Q of t are continuous functions of time, not much different from A of t or B of t in our first order differential equation videos. So over this interval of time, and we have two initial conditions right here. For whatever the initial conditions are at whatever the equation is, there is a function that exists and is unique, so there's only one for whatever specific initial condition is there. Notice that there's another initial condition. This is because we added another derivative to this, and so we basically need, like another initial condition for whenever we start plugging in stuff, like for this guy right here, and whenever we do all the crazy integration and all that stuff, which is much more difficult for this. We're not actually going to be doing integrating in this video, and whenever I'm going to be showing you whatever properties are going to be pretty crazy, pretty insane. We're going to be introducing some linear algebra in this video. But yeah, there is a solution for the initial condition. It exists. It's unique. That's all. Moving on, there's another concept called an operator. An operator is not much different from what we learned in pre-cal, where you have an f of g of x. So just a quick refresher, imagine we have a function called f of x that is equal to x plus 3, right? What do we want x to be? We just choose a number, right? So x is equal to 2. F of 2 is equal to 5 because that's 2 plus 3, right? Basically, instead of choosing x as a number, you choose x as a function, which is what an operator does. Here is the syntax for an operator, and so here is our function that we're going to be plugging other functions into. Here's an example operator, and the function that we plug into it is sine. The double derivative of sine is sine of t. The first derivative of sine is cosine of t, and then y is sine of t, right? So if, just to go back to another function example of it, if you want to do L of 3 of t, which would defeat the purpose of an operator, just make it a function at that point, then it would be 0 plus 0 plus 3q of t, right? So yeah, not much different from a function. So here's our first property. What we're going to use for these properties is to determine what I said earlier, linearity. With linearity, we can use these properties and even combine them to our advantage to help us find the general solution. General solution was not that big of a word when I was talking about the first order differential equations. We would reach the general solution by integrating, and there wasn't much merit to the idea of the general solution itself. I'm going to go more into depth on that now. And so let's start with these properties. Here's the constant property. Basically, this is just, there's a constant multiplying what's inside the operator, the function parameter for the operator. You can just take it out, right? Here's the proof for it. Remember, this is just very simple stuff. You can take out the constant, becomes a common factor. Sorry about the voice crack. It's just the common factor. the constant times the normal operator. Here. Easy. Then here's our addition property. This one is going to be very important. So here's the proof for that. Remember, the derivative of a plus b is just a derivative of a plus a derivative of b. So we have this. And then we can reorganize everything so that everything that's like related to y1 is on this side, everything y2 on this side. And then look, it's just our normal operator with y1 plus our normal operator with y2, right? And then so here we have L of y1 of t plus L of y2 of t, right? It's just easy. I'm going to show you guys now a non-linear operator, something that doesn't work. So first of all, let's just use the constant thing on that. L of 3y of t would be 3y plus 1, right? If we take out that constant, 3 times L of y of t, then that gives us 3y plus 3. Those are not the same thing. Already not linear. I'm going to show you guys how it doesn't work with the addition property. So let's have two new functions that we can plug into this called y1 and y2, right? So y1, if we plug it in, is going to become y1 plus 1. y2, if we plug it in, becomes y2 plus 1, right? So here, as I said earlier, y1 plus 1 plus y2 plus 1. This is the end of our addition property, if you recall. And so it gives us this. So what we're going to test for now is if, L of y1 plus y2 is the same as this, right? So when we do L of y1 plus y2, we're going to replace y with y1 plus y2. And then we get this. It's not the same as what we got on the last slide. So it's not linear. None of our tips or tricks are going to work. Boo-hoo. Too bad. I hate this operator. I'm just kidding. I love it. Guys, if I'm voice cracking for the rest of this thing, please don't pay attention to this. This is like take 47 of recording this video, so my voice is a bit shot. But yeah, here we are back to our second order differential equation, homogeneous. I've been saying homogeneous this whole time, and some guy commented in one of the first videos saying, dude, it's not homogeneous, it's homogeneous. And I was like, oh my god, I'm so sorry, I'm never going to do it again. And I just did it again. It's embarrassing. It's embarrassing. I'm sorry, guys. But yeah, here it is. But now it's linear. How do I know it's linear? Because we did all the proofs for the properties using this. So it is linear. Our linear second order differential equation that is homogeneous. Right? Homogeneous because there's a 0 on the right. It would be non-homogeneous if there was like another function on here, like an f of t or something. So yeah, this is linear. So how about we use our old tips and tricks and the properties on this, right? So let's say that there's two solutions to this, y1 of t and y2 of t. Why am I choosing two solutions? Here's the thing. This is a second order differential equation. That means it's going to have a two-dimensional general solution. Sensei kernel mathematics. What's a two-dimensional general solution? What are you talking about? I know. It's pretty crazy. I'm going to explain it a bit later. I'm not going to distract from my main points here. But so yeah, y1 of t, y2 of t. Basically, what this is saying is that if we make our operator here, if we make the parameter y1 of t, it's going to equal 0. If we make it y2 of t, it's going to equal 0. And so isn't, ly1 of t and isn't ly1 of t plus ly2 of t just equal to L of y1 of t plus y2 of t? That's the same thing, right? That's the same thing because we know that's this property for linear operators, right? And here's the thing, we're going to combine operators here too because we're going to add a couple constants in there. Here. I would just like to say that this comma is supposed to be an addition symbol. Like, we're adding them. So this works right here. So if you guys are taking notes, please just put an addition symbol. Sorry about that. Oops. Yeah. But so, yeah, if that is a bit complicated to you, just don't think about it too hard. At a certain, this is supposed to equal, these are supposed to equal 0, right? So when you do this plus this in the operator, it's 0 plus 0. When you add constants, it becomes a constant times 0 plus a constant times 0. So this does work. It just all equals 0. So yeah, nothing too crazy. So I'm going to show you guys a specific example. Let's set p of t equal to 0 and q of t equal to 1. So this whole thing is just going to vanish and die. And this will just, you won't see the q of t, it's just going to be y. Alright? Here we go. Here it is. Look at him. So nice and, what a cute equation, right? So let's find our y1 of t and our y2 of t. Here they are. Nothing too crazy. Cosine of t is, double derivative of negative cosine plus cosine is going to be equal to 0. Double derivative of sine is negative sine plus sine is equal to 0, right? Nothing crazy there. Yeah. So using our original, combining our properties, combining everything from the past few slides together, we have this right here, and we know that this works. This is a combination of solutions, a linear combination of solutions, independent solutions to this equation right here. I'm also going to call this equation the gamma equation, just because it's so much easier than saying, just saying all out, that one specific waddled down version of our homogeneous second order differential equation, linear. It's just, I'm just going to say the gamma equation, right? So, yeah. Is this the general solution, though? Guys, finding a general solution for one of these second order differential equations is going to be a hard task, because we're going to have to look into some things called linear independence and dependence. First things first, before I get into any of that crazy stuff, I'm just going to say straight up, there is another independent solution to this that some of y'all might have thought of. It's just 0. The double derivative of 0 is 0, plus 0 is equal to 0, right? The reason is, I'm not even going to proceed with 0, right? Because so this right here is our candidate, our shining candidate for the general solution, right? The general solution means that this right here, with our arbitrary constants, could be fine-tuned to be any of our independent solutions depending on what we make the arbitrary constants. Here's the thing. If I'm proceeding with 0, like just say in an alternate universe, instead of making my y1 of t cosine of t, it's just 0, because 0 is an independent solution, right? So this is 0 right here, plus c2 sine of t. What constant can I multiply 0 plus another constant that I can multiply sine of t to get cosine of t? Like, let's just disregard the 0 for a second, because we already know nothing's going to equal like cosine. Nothing times 0 is going to equal cosine. But like, what times sine is going to equal cosine? Nothing. Guys, it's going to be nothing. So we can already disqualify 0 from being in the running for this right here. For being our candidate for the general solution. Right? But here, cosine of t, sine of t. Let's change the constants. Let's make both of the constants 0. Then we get an independent solution that we can't even see in here. This is such a beautiful candidate. It's making me want to tear up. So I need to explain some theory to you guys. Solution spaces. What is a solution space? Remember what a general solution is. A general solution is the solution to the differential equation that can capture every single independent solution, or, like an independent solution, just depending on how you tweak the arbitrary constants. By the way, if you guys are wondering where the arbitrary constants come from, it's just something that comes about from integration. If you want to see that in action, like the combat footage of that happening, go to one of my earlier videos and I integrate a first order differential equation out to where there is the arbitrary constant on the left. So yeah, there is an arbitrary constant. Yeah. So yeah, that's what the general solution is. Basically, the general solution has to be able to capture a vast universe of every single one of the many solutions, independent solutions to the differential equation. Here's the thing though. The way differential equations work is that the higher you go in order, means there's going to be a larger space of, independent solutions that you can capture. Okay? So look at this right here. The first order differential equation is going to have a one-dimensional solution space. Think about it like a fishing rod. A fishing rod is a line, like one dimension. You can catch like, a couple fish on it, right? You can catch a couple fish with this, but we need to think bigger for the second order differential equation. We need to go up to 2 dimensions. Imagine that this net right here, I don't even know what shape it is from looking at it because he's throwing it. Imagine it is a square, right? You can capture way more fish in a square. You can capture every fish in a square. You need to capture every fish, right? Think about it like this. Think about the uh, space, the solution space for your second order differential equations general solution as a 2D plane. You have an x-axis and a y-axis. That x and y-axis together capture everything, the entire 2D plane for all of infinity, right? If you just have a half of an x-axis and a y-axis, you're not going to get everything to infinity, right? So that's the thing that we're looking at here now. Our two functions that we're going to use, that we're going to suggest for a general equation, which right now in the running are the constant time cosine t plus the constant time sine of t, have to be something called linearly independent. They have to be able to stand on their own. They have to be entire axes in themselves. The thing is, if either of them are something called linearly dependent, then they're only half an axis. We're screwing ourselves over. We can't get every single independent solution, so it's not a general solution, right? We need the whole fishing net. We need a good fishing net with a good foundation, right? We need the whole x-axis. We need the whole y-axis. We need to get everything. We need to get a whole general solution, right? So I'm going to show you guys how to actually find out if either of the functions we're looking at are linearly independent or linearly dependent. Here's a weird word for you guys. Wronskian. What is a Wronskian? What is this right here? I've never seen anything like this before in my life. This right here is a 2x2 determinant matrix. Basically, just for what a Wronskian is, like a general definition, it's basically a way to find out if functions are linearly dependent on each other or not. Basically, if you have n functions that you're trying to compare, you take all those functions, you calculate the n minus 1th derivative of all of them, and then, yeah, you just evaluate them like this. So, yeah, and if it equals anything but, 0, if it equals anything but 0, then your functions are linearly independent. But if it equals 0, it's over. It's over for you. So here's an example here. So here is our general solution for the second order homogeneous differential equation that's linear, right? The linear one. So here are our two functions in the general solution. And so 2, that's our n. What's 2 minus 1? It's 1. So we only take the first derivative of them. So here we have a 2x2 determinant matrix. How we proceed from here is that we cross multiply and then subtract. So we multiply this together, and then we subtract this from this. Multiply boom, boom, minus boom, boom. That's it, right? Nothing crazy. And so whatever this equals, if it's equal to 0, it's over. It's over. Whatever your y1 and y2 are cannot be the y1 or y2 that you're going to end up putting in your general solution, right? Here. This is our candidate right here. Our big, beautiful candidate who I've been rooting so much for this entire time. Cosine of t times, or the constant times cosine of t plus a constant times sine of t. I think that's the general solution to the gamma equation that I was talking about earlier. I really do think it is, right? So let's look at a Wronskian. Let's get the Wronskian of it. So y1 of t is cosine, y2 of t is sine. The derivatives of them are right here. Let's cross multiply them. Cosine of t times cosine of t is cosine squared of t minus sine of t times negative sine of t equals positive sine squared of t, right? I mixed up my words a bit too much on that. Yeah, and then we get this. It's equal to 1. 1, guys. So our candidates work. Oh my goodness, they work. I'm so excited. My candidates work. Guys, my candidates work. Yeah, but that's crazy, isn't it? That's how you do a Wronskian. I'm going to use this as another opportunity to dog on the alternate universe where I chose f of 1 of t equaling 0. Let's imagine we took the Wronskian of that. The right side would say it's the same because f of 2 of t is equal to 0, right? Oh, I meant to say y of 2 of t and all that. My bad. And so, yeah, so the right side is going to be this because y of 2 of t is sine, right? The left side is just going to be 0 across the board. 0 times this is 0. 0, or sine of t times this times 0 is 0. This is going to be 0 minus 0 equaling 0. So 0 is linearly dependent. Ah, that's embarrassing, isn't it? Won't work. It's never going to be part of the general solution. Never, ever, ever. All right. Here's another way to see linear independence or dependence. Well, after this, now we can conclude that this is the general solution. Capital G, capital S. Give him the Medal of Honor. Give him the Purple Heart. Everything. This is him. This is the honorable general solution himself. He won World War II for us. Yeah. Moving on. So here's another way to see it. If either of your functions are constant multiples of each other, then they're linearly dependent. It's over for you. Retire. Leave the planet. Go to Mars. So yeah, these you can't multiply cosine of t by anything to get sine of t. You can't multiply sine of t by any constant to get cosine of t. Look at this though. You can't multiply 0 by anything to get e to the power of t, right? You can't. E to the power of t will be constantly changing because of t constantly changing. So you will just, yeah. But vice versa. E to the power of t times a constant multiple equals 0. What is that constant? It is 0. No matter if e to the power of t at, t equals 70 billion quadrillion is like that the thing, times 0, it's going to equal 0, right? So this is linearly dependent. These functions are cooked. They can't do anything. They're never going to be general solutions. They might be independent solutions, but they will never be part of the fundamental set of equations that comprises of the general solution. Okay? So, yeah, here we go again. I do not know why that was a blank slide. Sorry about that. Yeah, so here is a combination of, so yeah, if y1 of t and y2 of t are linearly independent of each other, then this right here is the general solution to our linear second order homogeneous differential equation. Thank you, ladies and gentlemen. Thank you all so much. Thank you guys so much. So if you guys are also wondering why it has to be only two things, remember again that there's two dimensions to the general solution of, a second order differential equation. So there are literally only two linearly independent solutions. There's not three. There's two. So yeah, thank you guys. I hope you guys enjoyed the video. Yeah, more blank slides. Thank you guys for watching.